SI-1 for all hands full. Roger, SI-1. Welcome home.
I remember I was once making the crossing between Cape Horn in South America to the Antarctic Peninsula on a body of water named the Drake Passage, named after the famous explorer Sir Francis Drake. It had already been a superb day, relatively calm. We'd been able to easily spot humpback whales, fin whales, right whales, and even a pair of southern bottlenose whales. Normally, a sighting of any one of these species would have made the day special. And I was just sitting down for some well-deserved supper in the crew mess towards the end of the evening. I then got a call from the bridge of the ship. Another whale had been spotted, and they needed my help identifying it. When I reached the bridge, I could see that we were beginning to lose the light of the day, which also told me that whatever animal it was, it may well be feeding. In the twilight hours, prey comes to the surface to feed itself, and baleen whales usually take advantage of that behavior. Why dive deep for food when you can wait for it to come to the surface where you are? Suddenly, we heard the sound of a massive sonorous whale blow just under the bridge wing. I moved across the port side of the vessel and I watched carefully, and it was glassy calm, so it was easy to see the animal had a fairly flat rostrum, a long back, tiny dorsal fin visible just before the animal went below the surface. It was a blue whale, and it was spectacular. Perhaps 25 meters long, one of the largest species ever to have lived on this planet. It surfaced several more times, each time leaving a smooth patch of water in its wake caused by the down pump of its enormous flukes. We call these patches footprints, and by lining them up after each surfacing, we could guess where the animal would next surface. Because this animal was easily outswimming us, traveling at maybe 12 knots or more, it was hard to keep up with it. I had my binoculars trained on a patch of water where I expected to see the next surfacing, when I noticed a strange disturbance in the water. It was like seeing irregular raindrops falling on the sea's surface. I just had time to realize that in fact, these disturbances were tiny organisms flying out of the water before a massive mouth erupted out of the ocean, engulfing tons of water and whatever those tiny organisms were. "It's feeding," I yelled. "Lunge feeding." Now, lunge feeding is a foraging strategy where a baleen whale will chase after prey and trap it against the underside of the sea surface. And with a final flick of its tail, it lunges at its prey and overtakes whatever large mouthful of prey is waiting for it there. This is a particularly useful technique when the prey the animal is chasing is fast, as indeed this was the case. For this blue whale was feeding on krill. We've already talked about krill. Krill is a small shrimp-like organism, perhaps 5 centimeters long. It's a very important organism in the Southern Ocean. But what I want you to take away from this story is the act of a 25-meter blue whale, perhaps 40 tons in weight, feeding on tiny, tiny plankton, which in this case individually weighed perhaps 100 millionth of what the whale itself weighed. Plankton is essential to our oceans, and that is what we're going to talk about today. It forms the basis of the food web upon which all marine life depends. So it's really important to understand it before we move on to the larger species. The word plankton comes from the Greek planktos, which means drifter. This is a reference to the fact that plankton do not have the ability to move significant distances horizontally in the ocean, and therefore they rely on ocean currents to push them around. That said, many plankton species do have the ability to migrate up and down the water column, just as the krill in my story had done, coming to the surface at night. We can divide plankton broadly into two groups: the phytoplankton and the zooplankton. The prefix phyto means plant-like, and this is a reference to the fact that similar to plants, phytoplankton have the ability to photosynthesize. Phytoplankton include many species of algae, but in particular are dominated by diatoms and dinoflagellates, as well as many prokaryotic species. Among that last group are the cyanobacteria, which get called the blue-green algae, even though as prokaryotes they are not technically algae. In the term zooplankton, the zoo refers to animal-like. The majority of zooplankton do in fact come from phyla within the kingdom Animalia. However, some are from the group known as Protista and so are not technically animals. So in both cases, the terms zooplankton and phytoplankton can be confusing. This is mostly because we continue to change the way we classify life. And to help with that confusion, it may be useful to consider phytoplankton as autotrophs and zooplankton as heterotrophs. So let's look at those two terms. The term autotroph literally means self-feeding. And it's a reference to the fact that all autotrophs are capable of some kind of synthesis. That is, the conversion of carbon dioxide in the presence of water to sugar molecules using energy harnessed either from the sun, in the case of photosynthesis, or from other chemicals, in the case of chemosynthesis. In eukaryotic organisms, photosynthesis occurs in organelles called chloroplasts. Chloroplasts, in turn, house photosynthetic pigments that are specific to the species in question. Green algae, for example, contains mostly chlorophyll A and C. Red algae contains phycoerythrins. These differences result in the difference in external coloration. The sugar molecules produced by photo and chemosynthesis can then be oxidized or burned to release that stored energy. This oxidation produces a chemical known as ATP, or adenosine triphosphate. ATP is an unstable molecule that wants desperately to get rid of its third phosphate group. In doing so, it releases energy that can be used by the cell's metabolism. In this way, sugar molecules are simply temporary chemical energy storage units that can be used to generate ATP, the cell's energy currency. Thus, autotrophs are capable of producing the calorific energy they need to sustain themselves. In other words, they self-feed, autotroph. And while it is true that all phytoplankton are autotrophs, the converse is not true. In the ocean, not all autotrophs are phytoplankton. As I've noted in a different lecture, some halotolerant plants, such as seagrasses and mangroves, are important local contributors to the productivity budget. Also, some multicellular algal forms, otherwise known as seaweed, are anchored to the littoral or sublittoral zones and are therefore technically not plankton when in their adult form, although their gametes and spores would be. Finally, bacterial chemosynthetic autotrophs living within the sediment would technically not be planktonic. Now, let's move from the autotrophs to the heterotrophs. In general, heterotrophs do not have the ability to produce their own food. There is one small exception here. So-called mixotrophs are both heterotrophs and autotrophs at the same time, but we'll leave them aside for now. Heterotrophs must feed on other things to obtain calorific energy. This is what the term heterotrophy means, to feed on others. To do this, they can either feed on other heterotrophs or on autotrophs. Thus, as heterotrophs, zooplankton are by definition located higher up the food web than the phytoplankton. Let's start thinking a little bit more about that food web. Producers, or autotrophs, are at the base of the food web. They represent what we would call the first trophic level. The second trophic level, or the primary consumer level, is occupied by what technically must be heterotrophic herbivores, because they're feeding on phytoplankton. The third level, or secondary consumer level, is occupied by heterotrophic carnivores, as is the fourth, fifth, and so on, until we get to the apex predator, which is, in the marine world, is usually a large fish or marine mammal, or perhaps a seabird. I don't want you to get too hung up on the numerical value of these levels. In reality, a predator can feed across many trophic levels just as we humans do. What is more important is that the mapping out of predator-prey relationships in this way helps create a trophically dynamic system, so we can understand the interplay between organisms. And we'll talk more about this in another lecture. Organisms at each trophic level do not necessarily have to be consumed by the predators at the next trophic level. They can also die naturally. In this case, the dead organism can be broken down by bacterial action. From a chemical point of view, This is taking the various complex organic molecules that represent the organism in life and breaking them down to the simpler products. These products can then be reused by autotrophs as they continue to synthesize. For example, phosphates and nitrates are particularly important in regulating productivity reactions. We've already talked about the importance of oceanographic mechanisms in delivering those simple products or nutrients to areas where autotrophs can make use of them. In this way, phytoplankton is not homogeneously distributed across the ocean. Rather, their distribution is heterogeneous, organized around upwellings and other oceanographic focusing mechanisms. Thus, we can think of a food web not just as a linear, one-way directional movement of organic molecules, but rather a cycling. Each trophic level plays an important role in transferring their energy to the next level. In marine ecosystems, both the phyto and the zooplankton play an essential role in that regard. As humans, we tend to place value on organisms at the top of food webs, what trophic ecologists refer to jokingly as charismatic megavertebrates. But in reality, those organisms at the top are ecologically speaking no more important than the organisms at other trophic levels. So now let's return to the base of that marine food web and take a closer look at the phytoplankton. A majority of the phytoplankton are, as I mentioned before, algae, protists or prokaryotes. The algae fall into two kingdoms. Red and green algae recently have been reclassified as plants, and so we find them in the plantae kingdom as two separate divisions. However, there are also several important protist phyla represented in the phytoplankton, as well as a phylum of bacteria. We'll begin with the plants. There are certainly representative red and green, both single-celled and multicellular algae that would be considered part of the phytoplankton. Green algae, also known as chlorophytes, are interesting because many believe that they are the ancestors of modern-day terrestrial plants. Most green algae are freshwater species, but a significant proportion are marine. However, there are relatively few red algae, or rhodophytes, that are single-celled and planktonic in their mature form. Both green and red algae are commonly found in the intertidal zone, in multicellular forms we call seaweeds. You may have seen what we call sea lettuce on a beach somewhere. That is an example of a multicellular chlorophyte. And perhaps if you live in Northeast North America, you may have eaten dulse, which is a multicellular rhodophyte or red algae. Some red algae can even produce calcareous deposits that allow them to persist in highly dynamic environments. Confusingly, we refer to these species as the coralline algae, even though they are not coral. However, as most seaweeds are attached to substrates within the intertidal, they are technically not plankton until they become unattached and start floating around at the mercy of local currents. There is at least one form of free-floating seaweed that is technically planktonic, sargassum weed, which lives exclusively in the Sargasso Sea, trapped by the North Atlantic gyre. Sargassum is one of those brown seaweeds that belongs to a class that includes the kelps, rockweed, bladderwrack, and many of the other seaweeds you would see in the intertidal. But again, of all of these, technically only sargassum is planktonic and therefore part of the phytoplankton. That said, all seaweeds reproduce using motile gametes and disperse using spores that require water. These stages in life history certainly would be planktonic. If you live by the ocean, this is easy to prove. Take a clean acrylic pate and immerse it off the end of a dock for a few weeks. When you return, you'll find it has been populated by a number of animals and seaweeds that got there via planktonic dispersal. The slub on the underside of your boat, the slime on your mooring buoy, are all for the most part multicellular algal forms that have been dispersed planktonically. Now let's move away from the plants. The majority of single-celled eukaryotic phytoplankton in the ocean come from two specific protist groups. The first of these are the diatoms, which belong to the phylum Heterocontophyta. Heteroconts are a very broad protist group that also includes the golden algae and the brown algae. Diatoms are incredibly abundant. drop of surface seawater from pretty much anywhere around the world will contain some diatoms. They are extraordinarily beautiful in their external design. They possess silica-based walls called frustules that can be architecturally very complex and very ornate. We can broadly divide diatoms into two orders: the centrales, which have a round, radially symmetrical form, and the pennales, which are bilaterally symmetrical and have a pennate form. Photosynthetic pigments, which include chlorophyll A and C, as well as other xanthins, give diatoms a yellow-brown color. Diatoms are very common in the phytoplankton. It is thought there may be as many as 100,000 different species, many of them as yet undiscovered. Importantly, diatoms are not capable of individual locomotion in their mature form. Some use certain types of lipid that keep the cell more or less neutrally buoyant. Otherwise, they must rely upon upwelling ocean currents to keep them at the surface. A diatom that sinks into the dysphotic and the aphotic zones dies and quickly becomes part of what I've referred to before as the organic rain o' death, otherwise known as marine snow. Marine snow is a generic term given to the sinking of organic and inorganic particles through the water column down to the seafloor. And it is a major transportation pathway to deliver nutrients to greater depths. It's called snow because when divers shone their lights in the depths or took photographs with flashes, all they would get back were white dots, which were the reflections from each of these particles, rather like driving through a snowstorm with your high beams on. The second protist group is the phylum Dinoflagellata. The name, from Greek and Latin roots, means whirling whip, a reference to the two whip-like flagella that work to provide the cell with a weak twirling motion. This limited mobility is probably important in keeping the dinoflagellate close to the surface and therefore within the photic zone. Dinoflagellates can be divided into the thecate or armored dinoflagellates and the athecate dinoflagellates. The theca is similar to the diatom's frustule, a thickened cell wall made of cellulose that provides protection. The way the theca is arranged around the dinoflagellate is referred to as its tabulation, resulting in at least 6 different known configurations that aid in classification. Most also have a somewhat unique cell nucleus called a dinocaryon. Although dinoflagellates are considered eukaryotic, some believe the dinocaryon to be an example of the transition between a prokaryotic and a eukaryotic design of nucleus. Although they are not the only algal group to do so, certain species of dinoflagellates are notorious for their formation under certain conditions of harmful algal blooms, sometimes abbreviated to the acronym HAB, and often better known as red tides. Although it's unclear why they might do so, certain species manufacture extremely harmful toxins. The concentration of these toxins per individual dinoflagellate cell is negligible. But under the right conditions, say for example if nutrients and light are bountiful, the subsequent bloom can raise toxin levels per unit volume to dangerously high levels. Filter or suspension feeders, such as bivalves, which typically forage indiscriminately, are particularly susceptible to the accumulation of these toxins. And then, if humans eat those bivalves, say a mussel or a scallop, the results can be deadly. Perhaps the most notorious result of ingesting toxin-laden food such as this is PSP, or paralytic shellfish poisoning, caused by a poison known as saxitoxin, which causes temporary nausea, shortness of breath, and mental incapacity. In the most extreme cases, PSP can be fatal. And this is why local authorities constantly monitor for red tide levels in any area that is actively fished for shellfish. Living on the coast myself, I can tell you that closures are more frequent than you might think, but are often quite localized and fairly temporary. For us in Maine, the dinoflagellate genus of concern is Alexandrium, and the local Department of Marine Resources monitors its concentration religiously. For us, Alexandrium blooms appear to correlate with wind and storm activity that drive and focus the blooms into small inlets and bays that are home to intertidal shellfish such as mussels. But why is it referred to as red tide? Simply put, when it happens, The dinoflagellates breed at such concentrations that they turn the water red, almost the color of blood. In reality, it's just a reflection of the color of the photosynthetic pigments within the individual cells. Certain types of diatoms can also create a harmful algal bloom. These are called brown tides for similar reasons, although the types of toxins involved are different, as are the potential medical consequences. Of interest, some skeptics use red tides to debunk the story of Moses' God turning the Nile to blood. Their argument would be that Egyptian sanitation was probably quite poor, and that the Nile would likely have been very highly polluted with high levels of nitrate and phosphates, nutrients that might encourage a red tide. Also, anyone that continued to eat food taken from the Nile during a red tide could risk PSP in some form, which might explain increased mortalities during the time. It's an interesting idea, but I suspect we should leave the possibility of a dinoflagellate being an agent of God to a different course. Certain types of dinoflagellates form symbiotic relationships with cnidarians to form coral. We call these zooxanthellae. And confusingly, some dinoflagellates are also classified as heterotrophs, that is, non-photosynthetic, and some as mixotrophs, that is, they are both auto and heterotrophic. One species that perhaps you may have seen, literally, is the heterotrophic dinoflagellate Noctiluca. Noctiluca feeds on other phytoplankton, but it has an interesting side behavior. When you agitate it, it bioluminesces. If you've been on the ocean long enough, you will have seen this at some point at night, and the effect is magical, nearing supernatural when you first see it. The first time I saw it was when I was walking on the beach at night. The waves were crashing on the shore, and the pressure waves causing the transfer of energy within the physical wave itself could be seen as pulses of excited Noctiluca. The second time I saw it, I was on watch at night on board a sailing vessel in the Caribbean on a relatively calm sea. It was impossible to see incoming squalls because it was so dark, but nonetheless, you could tell where they were around you because the water immediately below the heavy rainfall would glow green from the act of the raindrops hitting the water, sending small pressure waves that excited the Noctiluca. And these mysterious green patches would migrate around me as the highly localized storms moved around the boat. The final component of the phytoplankton are the cyanobacteria, what used to be referred to as the blue-green algae, before we realized that they were prokaryotic in design. It is hard to overstate the importance of the cyanobacteria. They are an extremely ancient phylum within the domain bacteria, dating back perhaps as far as 2 billion years ago. And through their photosynthesis, they may well have been some of the very first organisms to start oxygenating our atmosphere, an event that had an incalculably important effect on the future life of our planet, which for the most part is now aerobic. Although cyanobacteria have photosynthetic pigments like eukaryotic photosynthetic autotrophs have, these pigments are not stored in chloroplasts. Recall, prokaryotes do not possess organelles. Rather, the pigments are stored in folds of the cell membranes. However, a very popular theory, known as endosymbiosis, suggests that eukaryotic cells were formed when one prokaryotic cell ingested a bunch of smaller prokaryotic cells. We are now reasonably confident that the chloroplast that we see in today's modern photosynthetic eukaryotes evolved from ingested cyanobacteria, possibly over 1 billion years ago. Also extremely important is cyanobacteria's ability to fix nitrogen, an ability known as diazotrophy. This means they can take the raw nitrogen gas of our atmosphere and convert it to metabolically useful compounds such as nitrates, nitrites, and ammonia. Nitrogen is an essential element in amino acids and therefore protein construction, as well as in nucleic acid formation. There is no other way for eukaryotic metabolism to get this nitrogen other than through the fixation process performed by diazotrophs. So one can see that the ecological role that cyanobacteria play is absolutely crucial. However, for many years it was very much overlooked, because phytoplankton studies typically did not look for organisms the size of cyanobacteria. A typical phytoplankton net has a mesh size of around 60 microns. That's about 6/100ths of a millimeter. With that mesh size, you will catch all kinds of diatoms and dinoflagellates. In fact, in a particularly productive area, they'll gunk up your net. But a typical cyanobacter is tiny by comparison, perhaps only 0.001 millimeters. That's a billionth of a meter. So they easily slip through this kind of mesh. For this reason, for many years, we underestimated the potential productivity of the ocean because we were only counting the eukaryotic cells. Now that we have the techniques to capture the prokaryotic portion of the phytoplankton as well, what we sometimes refer to as the nanoplankton, our estimates of the overall photosynthetic budget for the ocean are nothing short of astounding. It is based on that productivity that pretty much all ocean life exists, at least that portion that occurs in the photic zone. But also recall the basic photosynthetic equation takes water and carbon dioxide, and under the conditions of light and nutrients, converts those reactants to a sugar molecule and oxygen. That's what I meant earlier when I noted that once the process of photosynthesis began on our planet, our primordial, once anoxic atmosphere slowly began to increase in oxygen to the state that we have today. So in a way, the amount of oxygen that we have in the atmosphere and dissolved in our oceans is a proxy for how much photosynthetic activity is actually happening. Take a deep breath. Enjoy the oxygen you are now breathing. Now, where did that oxygen come from? To some extent, it came from terrestrial plants around you. But at least 50% of that oxygen comes from phytoplankton, even if you live in the center of a country. And within the phytoplankton, probably about half of that comes from diatoms alone. Now, I'm not sure I can think of a better reason to respect our oceans and try to keep them as pristine as possible. That oxygen fuels our planet. Without oxygen, most life on this planet would die. When we think about ocean preservation, we often adopt token animals that can act as the poster children for our efforts. For example, who hasn't heard of Save the Whales? Sure, seems like a good idea. Or Save the Turtles. Yes, that would be nice. Save the albatross. Of course, who wouldn't want to save the albatross? But above all else, we should save the phytoplankton. Because without phytoplankton, this would be a very different planet indeed.